All right, now that we have laid a solid foundation on NMRO spectroscopy, let us now try and draw some NMRO spectrum. All right, what we are going to do is to draw NMRO spectrum. Now we say the NMRO spectrum, there are certain things that we should be cognizant with. And one of those things is the different chemical environment of protons. Now, each of these chemical environment of these protons, they have different chemical shift values. As you can see here, these are protons in different chemical environments and the expected chemical shift value. You can see that a proton that is attached to an alkyl group in such a way that it's a CH3 proton, the chemical shift value will be 0.9. Now, if it is a methylene group, this group here is a methylene group, that is CH2, the chemical shift will be a little bit around 1.3. Then, this other one here, the chemical shift is around 1.5. This is for a methyne group. Then, whenever you see a carbon attached to a carbonyl, of course, you should expect an increased chemical shift. Why? Because this oxygen here is what? Is negatively, is electronegative. Are you getting it? So there will be a shift, a downfield, or let's say downfield shift, right? And then this Cn also is electronegative. You have an increase in chemical shift. Bromine is electronegative, increase in chemical shift. OR is electronegative, increase in chemical shift. And then this group here is also, there is an increase in chemical shift. Is that okay? Now let us practice some questions. You have something like this. You are given something like this. Let's say H, C. This is a compound given to us. Let us predict the NMRO spectrum for this compound, right? Okay, this 3, C double bond O, and then we have C. Here is H, here is H, here is H. Now you have this compound here. Let us predict the different chemical environment here. Now, if you look at this very well, you agree with me that this CH3 proton are in the same chemical environment. That means this hydrogen, this hydrogen, this hydrogen, they are attached to this carbon, the same chemical environment, right? So they will actually come as one peak. Now, but we said that the protons in a particular, the protons, the peak you are going to get, right, is not due to the protons attached to the particular carbon, but due to the neighboring protons attached to the neighboring what? Carbon. Is that okay? So what I'm going to do, I'm going to have here, if you look at this, this is a different compound. This is a different chemical environment entirely. So I'm going to name this A. Now, there's no CH3 proton. There's no proton here. There's no hydrogen here. Because what we're actually talking about is a proton NMRO. So here is A. Here is what? B. Here is C. Here is D. Everything you have here, they are different. Are you getting it? They are different protons entirely. Now, a proton that is in the same chemical environment, I'm going to show you something similar to that. Now, the next thing we are going to do is to rule a straight line. Now, you don't need to actually draw the exact or write the exact chemical shift values. All you need to do is an approximate value. Is that okay? So let us take the first one. Let's take D. This is due to D here. Let's take this D. Are you getting it? If we start from A, the reason why I don't want to start from A is because A is attached to an electronegative atom. So you should expect A to be far as compared to D. So we are starting from somewhere here. Here is 0, right? Now this 0 has a peak that correspond to what? Tetramethylsilane, TMS. Is that okay? Now, if you draw for, let's say, or let's start with A in that. No, I don't want to start with A. Let's start with the one that will have lower chemical shift by numbering. Or we can number the something like this. I want it this way. Let's number it this way so that we can easily start from A. So here will be A, here is B, here is C, here is what? D. Now if we start from A, now you look at the neighboring carbon. How many protons are in the neighboring carbon? This is A. Are you getting it? That's 3 protons. But how many protons are in the neighboring carbon? The neighboring carbon is what you look up to, not the A itself. Now, you agree with me that A has 2 protons. Now, by the n plus 2 rule, you are going to add 1 to it. So this becomes 2 plus 1. 2 plus 1 will give us what? 3. 3 is a what? A triplet. Are you getting it now? And of course, the CH3 protons, they usually are absorbed at around 0.9. The frequency is around the chemical shift is around 0.9. So you are going to come here and indicate here 0.9. And then I said it's going to form a triplet. Because the multiplicity we are talking about, you consider the neighboring atom. Are you getting it now? Which is 2 protons, this and this. Directly attached, not the one far from it. You are considering the neighboring atom directly attached, which is 2. I told you by the n plus 1 rule, you usually add 1 to it. So 2 plus 1 is 3. So it's going to form a triplet. And if you look at the Pascal triangle we learned, told you that the triplet will be something like this. A triplet, we have a peak upward, and then it will have 2 other small this thing attached to it like this. This is what a triplet looks like. Is that okay? At 0.9. Then we have CH2 group. At what position does CH2 group actually? So this is what? A. Now you may decide to indicate it with A, right? Or you may decide to indicate the integral. Now, how many protons actually give this thing here? If you count, how many protons are present in A? 1, 2, 3. That is what gives you the integral. So you're going to have something like integral 3H, telling you that there are 3 protons in H. That means this thing here is due to these 3 protons. But what actually gives the multiplicity is the neighboring carbon. Is that okay? Now, the next one we are going to look at is B. Now, B we absorb at around 1.3. That is the chemical shift for B, 1.3. So we have it here at 1.3. Now, but if you look at B, there are 2 neighboring atoms that B have. What are the neighboring atoms? It has this carbon atom here. This is a neighboring group. And also this is a neighboring group. So B has 2 neighboring groups. When you talk about neighboring group, are the group that are directly attached to it. So B has 2 neighboring groups. Now how many protons in total? This is 1, 2, 3. Is that okay? Plus these other 2 protons here, 3, 4, 5. Are you getting it now? So you are going to have 1, 2, 3, 4, 5. That will actually cause the multiplicity in B. Do you get it now? So according to what I told you, it will be 5. But you are going to add 1 from it, from the n plus 1 rule, which is 5 plus 1. 5 plus 1 is how many? 6, which is a sextet. Are you getting it? Now for a sextet, what you actually have is something like this. You are going to have 6 of these lines, right? 2 will be of equal height. From Pascal triangle, we've actually looked at this. 2 will be of equal height, and then other 2 will be of equal height, and then you are going to have the last one like this. So this is a sextet. So you are going to come here and put, see that you put B to indicate. So so long you've numbered this, you can decide to put B. Are you getting it? Or you can indicate which of the carbon or which of the proton actually causes this splitting you see here. Of course, it's this CH2 that we are representing here. Is that okay? So you indicate integral 2H. Is that okay? And then the next one is another CH2. But this CH2 is attached to a carbonyl. And because of its attachment to a carbonyl, it's expected that the CH2 will be downfilled, because as you come here like this, it is actually increasing. Will be downfilled as compared to the other one. So this one is around 1.3. We should be expecting this one. You can see the carbonyl here. You should be expecting it at around 2.5. So you have this at 2.5. Can draw it here. Now, how many? Look, which of them is the neighboring carbon? Of course, you can see here is a neighboring carbon. Here is a neighboring carbon. To this C, we are looking at this C. This is a neighboring carbon. This is a neighboring carbon. This last one here is not a neighboring. When we talk about neighboring carbons, are the ones directly what? Attached. Is that okay? So we have that. Now, at this point in time, you are not going to think. This carbon here does not have any hydrogen, so it will not cause splitting. However, this carbon here has 2 hydrogens. And by the law, we said that whenever you have 2 hydrogens directly attached to the carbon you are considering, you add 1 to it, which is 3. So this is going to form a triplet. And by virtue of what we know that a triplet would be something like, a triplet will be something like this. Now, before we even talk about a triplet, there's something I want you to look at. So 2.5 is around somewhere around here. So it's going to cause, let's put 2.5 somewhere around here. 2.5, and then it's going to cause a triplet, right? You are going to have it something like this. What did I say concerning triplet? It's going to be 1, and here will be what? 2, right? This is a triplet. Now, you are going to write which of the carbon actually caused this. Of course, is C. And how many hydrogens are there? 2 hydrogens. So you put 2H to indicate the what? Integral. Now, the last one we are going to look at is this one here. Are you getting it? Now, if you look at this one, the neighboring carbon, does it have any hydrogen? No. So our N is what? 0. 0 plus 1 will give us what? 1. So what does this mean? If you look at, we are talking about carbon D. The neighboring carbon here does not have any proton. Are you getting it? So our N is 0 plus 1, making it 1. So it's going to be a singlet. But if you look at D, D is CH3 group. Where does CH3 group usually absorb? Or the chemical shift, where do we see it? Around 0.9. But because it is close to this carbonyl, to be a little bit just above this 1.3 because of the closeness to the carbonyl. Is that okay? So you are going to see a singlet that will be somewhere around here. So you are going to see a singlet. Is that okay? Which we can give it any value. We can say let's put it at 1.9. Because normally a normal CH3 is supposed to have a chemical shift of 0.9. But because of its proximity and closeness to this carbonyl, because which an electron withdrawing group, it will deshield it downfield. Are you getting it now? So this is downfield. Why this is what? Upfield. Now, if they ask you, draw the HN spectrum of these compounds with reasons. These are the reasons you are going to be writing down. Like you are going to say label first A, B, C, D. Carbon A have the HN Why? Because it has 1 neighboring carbon, and the neighboring carbon has 2 protons. By N plus 1 rule, 2 proton plus 1, making it how many? 3. So it's going to be a triplet. And because it's CH3, it actually have a chemical shift of around 0.9. That is why you have this one here. Those are the reasons. So when they say draw the spectrum with reasons, that is the reason they just want you to do. Then you come to B. You now say carbon B has 2 neighboring carbon, right? And each of the neighboring carbon, one has 3 protons, the other one has 2 protons, a total of 5 protons. 5 plus 1 by the n plus 1 rule will give us 6. So it's going to be a sextet. And then, because it is a methylene carbon, which is CH2, it absorbs around 1.3. That is why it is here. You state that reason. And then you say this is carbon D. This one here is what? Carbon D, right? Carbon D actually has one neighboring carbon, but that neighboring carbon has what? No proton. So it will be 0 plus 1, which will be seen as a singlet. And CH3 is supposed to absorb at 0.9, but because of its close proximity to this electron withdrawing group here, the electronegative atom, what will happen? It will shift it. It will be deshielded more, which will shift it towards this direction. Those are your reasons, and then the same thing, reasoning for this last one. Is that okay? All right. Let's see. Let's see. So that is that for this particular one. All right. Let's see for this one. Let's see for this one. This is almost the same thing with the one we just drew just now. We just wrote, but it's actually an isomer. What do you think the the proton NMR, what do you think it will be? You have something like this. Here is C, here is H, here is C, here is H, here is H, here is H. Now, if you look at this thing very well, you agree with me. If you look at it very well, now you agree with me that this stuff here is in the same chemical environment with this stuff. When we talk about the same chemical environment, we're actually using this to measure. If you look at this thing very well, this C double bond O, right? To this side, you have one carbon with CH2 before you have this. To this side also, you have one carbon with CH2 before you have this. So it means this group here and this group here are in the same chemical environment. And groups in the same chemical environment, they actually have just one peak, one absorption. Is that okay? They have one, this thing that you will see, one line, not just one line, but they have one peak that you are going to see. Are you getting it? Now, if you also look at these two things, to the right of this one, you have CH3. To the left, you have CH3. To the right, you have CO. The same thing applicable here. To the left, you have CO. While to the right, you have CH3. So these two groups, they actually have the same thing in their environment. Just more like mirror images. So we can say that they are also in the same chemical environment. Now, how do you know if they are the same chemical environment? You discover that if you rule a line through this center here, you agree with me that what you have here is also what you have here, right? So these two things are in the same chemical environment. These two things are in the same chemical environment. Is that okay? Now, the next thing we are going to draw now is a straight line to show. Now, let's take A and then draw. A is CH3. So we are expected to see, if this is 0 point, we are expected to see it at around 0.9. Is that okay? We are expected to see it at around 0.9. So what will the signal look like? Now, the signal, this is CH3. We say we consider the neighboring. The neighboring carbon here has 2 protons, which is N is equals to 2. So 2 plus 1 will give us 3. So it's going to be a triplet. If you also consider it from this side, the neighboring carbon has 2 protons, right? Plus 1 is going to be a triplet because they are in the same chemical equivalent region or environment. You are going to see just one signal for both of them. And that signal will be a triplet. So you are going to have something like this. How do we draw triplet according to the Pascal triangle I gave to you? Triplet is more like something like this. All right? That is a triplet. Now, also B. B is close to carbonyl. Normally, this is supposed to be at around 1.3. But because of this proximity to the carbonyl, we are expected to see it at a little bit higher than 1.3. So at what point proximity to this carbonyl, we are supposed to see it a little bit greater than 1.3. So at what point are we going to see it? Now, first of all, let us look at the neighboring. The neighboring to this side has 3 proton, right? The neighboring to this side has no proton. So 3 plus 1, making it a what? A quartet, which is 3 plus 1, which is what? 4. So you're supposed to see a quartet. The same thing applicable here. To this side is 3. To this side, no. 3 plus 1, 4. Quartet. So you are going to have a quartet. And because CH2 normally is supposed to be at 1.3, but because of its proximity to this compound, you are going to see it at around, let's say, 1.7. All right? Let's just put it at around 1.7. So you are going to see something like this. All right? Or, yeah, 1.7. You're going to see something like that. A quartet, the signal here will be very, very obvious. Are you getting it? Because of you have 2 things actually bringing that signal. Even this one will be very, because there are 2 protons, 2 different groups bringing up this signal. So a quartet is something like this, right? And then you are going to have this one here attached. This will now be called what? A quartet. Now, you can decide to say this is A, this is what? B. Or you use the signal notation. For the signal notation, what is this one due to? It's due to CH3 group. So you say, integral notation. This is due to 3H. Why this one is due to how many proton? 2 proton. So you say this is what? 2H. And of course, you can state your reasons why, right? Based on reasonings that we have actually given since. All right, so that is that. Now, we can also draw for the other isomeric pair that we have there. The last one. The last one we have C. It's kind of looking jaga, but we are still going to draw it. C double bond O, and then you have C, H, H, H. And then you have this one, C, H, H, H. Then you have this one, C, H, H, H. Now with reasoning, based on what we have learned, of course, this point here is 0 for TMS. Now, these 2 are in the same chemical environment. Do you know why? They are attached to the same carbon. Are you getting it? And what is adjacent to them is the same. So these 2 compounds here are in the same chemical environment. So you can say this one here is A, and this one here is also A. Are you getting it now? They are both in the same chemical environment. Now, how about this one here? This one is B. They are in different chemical environment. Now, if you look at them very well, what do you think can be done here? Now, there was something we forgot to note in this structure. There's a proton here. Are you getting it now? There's a proton here. So if here is A, now you agree with me that here would be B and here would be C, right? Good. Now for AA, what is the neighboring carbon to these 2? If you look at this one, the neighboring carbon to this is this carbon here, right? Which has 1 hydrogen. If you look at this one also, the neighboring carbon to it is this carbon here, which also has 1 hydrogen. That's why we say they are in the same chemical environment. It's more like this structure is a little bit looking confusing. This structure is the same thing as you have C double bond O. Here is what? CH3. Here is supposed to be CH. Here is CH3. Here is CH3. So if here is A, B, C, these 2 things here, they are in the same chemical environment. Why? Because they are attached to a carbon having just one. Are you getting it? They are in the same chemical environment. If you look at it very well, are you getting it? Now, the reason why they are in the same chemical environment is if you look at the carbons that is adjacent to them, is the same. This one has one proton. This one also, the carbon adjacent to it has one proton. Hence, they are in the same chemical environment. So they are going to show one signal. And the carbon that is present there is 1. It has one proton. And by n plus 1 rule, to be what? 1 plus 1, which is equals to what? 2. So this one is going to show 2 signals. Is that okay? Which is this. Is going to be very intense. And it's CH3, so you are going to see it somewhere around 1 or 0.9. There are 2 of them, so it's going to be a doublet, which is something like this. It's going to be a doublet. All right? Exactly. Now, the next thing we ought to look at now is this B. Now, if you look at B very well, what can you actually see with B? You agree with me that B is CH. And we say CH absorb, or it has a signal at chemical shift 1.5, right? But because of its proximity to this CO group, it's going to be far away from 1.5. So you are going to see it at around, let's say, 2.5. Let's say 2.5. You are going to see it at around 2.5. Now, listen. If you look at this very well, you agree with me that this CH is having just one proton. So this thing you are going to see there, the signal you are going to see there will be very, very small. Are you getting it? The signal will be very, very small. But there will be plenty signals. Why? Because of this splitting. Are you getting it? Why? Because if you look at this carbon here, with this proton here, the neighboring carbon, this one has 3. This one has what? 3. We are looking at the neighboring carbon to determine the multiplicity. So 3 plus 3, making it how many? 6. And by law, 6 plus 1 will give us how many? 7. So we are expected to have 7 signal. And I told you that when we are having 7 signal, you are going to have 1 signal. Now, the signal will not be that big. Why? Because it's just 1 hydrogen present there. So you are going to have something like this. All right. Then you are going to have another one. This 7. So, right. And then you are going to have another one. And then lastly, making it how many? 7. This is 1, 2, 3, 4, 5, 6, 7. So this will be the signal. And what proton is giving this signal? Of course, is just 1 proton. So you have H. Or we can label it as what? B. So this one is A, this is B. Then we have C. It's a CH3 proton. Now, for CH3, it's around 0.9. But because of its close proximity to this, we'll be seeing it at around 1 point something. And if you look at it, it has this neighboring carbon, which has no proton. We say when it has no proton, it will be 0 plus 1, which is how many? 1. So it's going to come as a singlet. But because it's for CH3, it's going to be very, very conspicuous for us to see. All right? So the number of proton actually tells you the intensity of what? This thing you are going to see here. So this here will be for, let's put it at 1.5. It's not supposed to be up to 1.5 because this is 0.9. But because of its proximity to this electron withdrawal, I've explained before. Now, whenever you have electron withdrawing group, they tend to de-shield it. That is the word to use. Is that okay? So you are going to have something like this. So that is that for this particular one. Thank you very much for your time. In the next lecture, we are going to elucidate more structures.